So welcome everyone. Thank you for making efforts to join me this morning at the UK, okay? So I want to use this title, Network and Geographical-based SpaceTime AI, to wrap up our recent work in this area. So, and also, it's also kind of my thoughts about recent GIS development and where it can go as one of the possibility. So within this hour, I'm trying to give you some background why we want to talk about network-based space-time AI. So what's the challenges and the progress we have made, and then summarize it and say where we can go further. So why we talk about network-based space-time AI? So because this is a GIS conference, so let's have a look what has been passing with what have been happening with GIS. So when I give a lecture to our MSc students, I think probably most of you guys giving lectures to your students, you probably start with this slide. So we will know, especially at this moment, I think the Dr. John's law has been mentioned many times, even now. So this is a map manually made by Dr. Slow, so which was in 1854. So he kind of identified or found out, say, who are those household has been, which is indicated with these small lines, has been affected by this cholera almost 150 years ago. So with that, he associated those households with this little pump on Broad Street. So he actually say, yeah, probably because of the handle of the pump, actually people are affected. And also this have a very strong implication for the sewage system of London. So in GIS, we claim him to be the first person use GIS for analysis, but for epidemiologists, they think it's the first epidemic analysis. So actually, when we really say of what is real GIS, probably we want to claim actually is Roger Tomlinson, who did his PhD in UCL geography. He really is the first person proposed using computer to draw maps. So at that time, I think it's 1970s. So what we got at that time, we have some information about the location X, Y, and we have some information of the terrain height. So most of our information is two-dimensional except team. So we talk about representation, storage, and we use the term spatial analysis. So I use this one red representing the data, and what we do use the green, and what the term we use at that time, use the blue color here. So then another 10 years, we started with the development with the web. So we have web-based GIS. At that time, we use the term digital S. We start Google Map. Then we also have OpenStreetMap. So very proudly, we call the founder of OpenStreetMap was created, started from UCL. So he was the original geography student, and then later on he was moved to computer science. So it's a good combination of both. So at that time, we have information, location of more images, and also we really have three-dimensional data as well in space and time. At that time, a lot of folks also really combine GIS with image processing, and also we use the term image understanding. And at that time, also Stan Openshaw, James also showed that book, AI in geography, and also started time geocomputation. Of course, we also have AGI, cyber GIS. Then move on, then with the smartphones, we have pervasive GI, and then we have real-time information, and then we start navigation, locational-based surveys. We call ourselves mobile GIS. Then next one is where we are right now. Actually, start, I think, of course, this is 2013, maybe a little bit early. We have Internet of Things with social media, with clouds, with big data, and then we have the term AI coming back because further development of the computer. AI has been there for a very long time, but now it's getting more popular, especially with deep learning. And then we have term GeoAI. I think this officially should be most probably starting from last year. And we call ourselves SpaceTimeAI. Okay, so I gave you the reason why, because space-time, as James explained as well, we have lots of data. We're not only talking about the location or about the time. And actually, time is crucial. And yeah, so that's where we are. So, because under the Internet of Things, actually, you can say networks right now has been everywhere, from GI network to social network, you learn it to transport network. So we are in the area of networks. So probably that's one of the reasons we want the network-based. But actually, more than that, I think the theme of this conference is AI and urban analytics. So lots of things were happening is urban analytics. What is really urban? So actually, urban is a place connected by networks. So from a practical perspective, so when we do navigation, we want to go from A to B. We have to put them on the route, on the network, not on other, we call the point line or polygons. So in terms of the granularity, we have fine granularity, we can give you also much accurate, if we talk about prediction, market rate prediction, and also analysis. I think another very important aspect is, I think on networks, modifiable areal unit problem is much less. You can, for the scale, very important. Of course, this is also another concept proposed by Stan Openshaw. So great mind. Yeah, so this issue can be avoided somehow. So it's the next kind of strength or advantage and motivation for us to do network-based analytics. So we talk about space-time AI. So what is space-time? I think we all know now is relevant to space and time. What is AI? I mean, there's lots of definition about or analytics or intelligence. So I pick up this one, which I think it really says well, fitting what we are doing here. So it's related to complex analytics, including modeling, optimization, and visualization. Really, the purpose is for operational decision making. I mean, we look about AI, people use a computer to do something humans can do, okay? So in my talk, I'm going to focus on what are the things that we majorly will think our lab really good at somehow, is to do the modeling and the forecasting, and of course, what's relevant to clustering and the simulation. So that's the background. Now, what's the problem? What's the challenges? Why we need to spend efforts to do that? So let's have a look. So actually, if we talk about networks, I think this is what you're very familiar with. We usually have point and the polygons, A, B, C, D, E here. We'll have networks on the right color because, yeah. So let me show, of course, have a pen so you can see one. So yeah, so basically you can see this is the, yeah, everything you can use the graph to represent it, okay? So that's very easy. What is really behind that? So we can basically turn a network into a graph. So this you all know it well. So basically you can turn a load into a load, or you can turn the edge into a load, vertex in the graph. So you already know all about it. So how you define networks, that's what I'm showing here. Yes, there's loads here. Then A, B, C, D, put them into or adjacency matrix. I think you're all very familiar with this adjacency matrix. That's one thing to represent the topology, okay? And then another thing we do, we have to measure how strong the adjacency is, or how strong the spatial objects are correlated. So this actually reflecting the first law of geography in a sense. So lots of different measures about the spatial weight. So we need the adjacency, we need the spatial weight matrix. So this you are all very familiar with. I think Morin's eye has been used to talk about the spatial autocorrelation a lot. So you're all familiar with. So that's all very simple, right? We got the graph, we got the adjacency matrix, and we also got the it turns into spatial weight matrix. So what's the challenge? So before we can really move to the most of the ones deep learning, let's have a look what it has been really developing in terms of integrated spatial temporal modeling. I think I want to start from this one, STARIMA. So this STARIMA, I don't know how many of you guys are doing spatial temporal modeling, but let me start with this one. So if you look at this formula here, actually this is the paper published. I think this is quite a famous paper by Philip and Stewart, which was in almost 40 years ago. Okay, actually almost 40 years ago, so it's a long time. So if you look at this formula, I think this is a really beautiful formula. Why I'm saying that, if you look at this, if we take out t, or take out the t and the k, or completely, and I here, I means location, t means time, okay? This is, h means the spatial adjacency. Say first order, second order, that means first adjacency, second adjacency. So W means space, representing spatial with the matrix just mentioned. So if you take out the t, so that's become our spatial regressional modeling, okay? So many forms can be further divided from that. If we take out this k or I, it become a RIMA. That means for time series analysis, okay? So what is showing is two parts. One part is called the auto-regressive part. That's the part related to your historical observation. Moving average is means error bit related, and this is the last-based residue, okay? So what is the problem with this one? Well, the challenge, to fit in a model into this formula, you request we call the weak stationarity. What does that mean? Means say you should have equal mean. So everywhere should have the same mean. So that means everywhere should be the same. They should have the same trend. Or there's no trend there, no change. Okay. And also you have equal similar standard deviation. That means you shouldn't have a peak. You shouldn't have a high, large difference far away from your mean. So we will know this is quite difficult to satisfy, isn't it? So that's the kind of one of the challenge. Okay, so because when I talk about this, I say you should have same mean. That means everything should be similar. But equally, they said everything far away should be more different. But that means there's a fast law. But this formula actually say, no, you shouldn't. You should be more or less the same. So that's the challenge. Okay. So because of this, we actually extended this formula standard STARIMA into what they call a localized STARIMA. So what is it doing in there? So basically, if you remember, we added one more thing to W, which is the time. And so is the time here, T. And also we add I here, which is the location. So that means with this spatial weight matrix is changing with the time and with the location. So what does it mean? Dynamic. So what dynamic means? Two things. Further say, yeah, it's changing with the location. That means spatial heterogeneity. And the changing with the time is the temporal dynamics. So this dynamics can be including even the adjacency itself. So when it's highly congested, your spatial adjacency can be less. But when it's very smooth, that means the flow upstream, downstream can go very long way. So of course, so is the weight, okay? So that's the challenge. So even we developed this one, we still found it's quite the accuracy or how to fit in this model is quite a challenge. So that's all the kind of thing actually in terms of space and time. If we put it into networks, so I think that's the challenge. The dynamic spatial weight matrix, how to capture this and to put it into your model. That's the challenge. Okay, so that's the conventional statistical approach. Now we are in the area of the AI with deep learning. Okay, so what is deep learning? So actually, it starts from what we call they say AI, including machine learning and the deep learning. Okay, so typical machine learning means this bit. Simple neural network. That means to say you have input, You have output, you have only one layer of hidden nodes, okay? Deep learning is this bit. That means you have multiple layers of this network, and they have multiple hidden layers showing here with these yellow dots. So what is really happening in neural network? Because some people did ask me, Tao, can you tell me the conventional, regressional, statistical approach? Why machine learning do better than statistical approach? Let's have a look. What has really happened in those hidden neurons? So basically, it's the same. If you talk about it, you have some input here. That's all we have fitting any model. But then you have a weight, okay? That's the weight you can say, think about the W I put into the ARIMA model. And then most important is this bit, is a bit activation function, okay? And then, of course, you have sum them up this one. So what is this? So most important one, there are many things that we call the bias wants to do something. Let's look at the activation function. So activation function actually is doing the many different forms of this activation functions. So basically, because of those activation functions, and because of there's multiple loads, they are able, the combination of them actually can simulate most complicated patterns. And especially with this multiple layers. So they are able to, if you talk about mimic, most sophisticated behavior. So that's what it's doing. So that's the strength of neural network compared with conventional statistical regression approach. Those are, most of them are linear regression, although you can make them more sophisticated. So I think that's the simple way, layman way to explain it. Okay, so in deep learning, when we talk about deep learning, I think there are a few models. I think the typical models, they start from the simple ones, artificial neural network, and then later on they have a recurrent neural network. So recurrent means feeding back strategy. And then later on, they have this long short-term memory. That's the one everyone talk about. So what is it? So basically, it has some internal mechanism called the gates. Those gates are very powerful. They kind of can learn, say, should forget, should store, or should update outputs so that the information, so the pattern can really be learned effectively. Okay. So what they really do, they really mean to say they can learn based on what happened in the past. Then they also understand the shorter term pattern and with long-term pattern. So this has been widely used for natural language processing, for prediction, for translation. Okay. So as you can see, LSTM can be used widely for time series analysis. Another one is this, what I call CAN, is a convolutional neural network. For anyone who have done image processing, they will understand the convolution. So basically, what is showing here, there's a standard convolution operator. It's just say you have, that's the operation here, okay? And then more than that, they also have called another strategy called multiple layers. That means you can summarize your patterns to that dimension. So it's very powerful. So I see this really makes use of the adjacency information on your images. So that has been used largely for facial recognition, object recognition, and object detection. So of course, if we use it for spatial, of course, we can be used for spatial dependency modeling. And the most latest, as I showed you, there are lots of networks available around because those structures are not really suitable for network-based structure. So graph convolution network, which we call the GAN, GCN or GNN, okay? So they have been developed. So basically, so this is really showing, say, you have a graph, okay? You have your the first level adjacency, first order adjacency, and so this is. Then you have your second layer adjacency where you have hidden layers. So anyhow, I think the details you can have a look yourself. So again, so this is based on the network structure to define what's going on. So they have these different structures. So how we put them into spatial-temporal learning? So actually there are several ways. So one of them could say, depending on the nature of the process, like a transport, we think temporal domain is very strong. So you could put these spatial operators into our temporal modeling layer, or the other way around. And another way, it could be a completely hybrid approach, like what we're showing here. You can first do spatial layers, then later on you can do temporal layers. So there are different approaches you can do, okay? So let's look at what have been done. So how to do it? So this is, as I said, originally mostly is the CNN convolutional method has been used because we get used to use the grade, and then this is an example of using transport flow. So we divided the space into grades, and then we into the, so that's the grades. You have the info, and that's the final outcome. So we want to put them into model. So if you look at here, so this bit is historical observation, then you have a model, then you have the outcome. So what do we do? So we put them in the model, as I said. So if you look at here, look at this diagram. So at the top, we have weekly input. So basically, we, as I said, for transport, actually, in terms of the cycle, you can differentiate them as, say, short term is the hourly pattern. Then you can also have a daily pattern. Say Monday is different from Tuesday. Tuesday different from the rest of the week. Of course, weekend is different from the rest of the week too. So you have daily patterns, and you can even say yes. This is weekly patterns. A daily input means to say morning peak. It means to say from 6 to 9 is kind of traffic is getting free flow to congested. And after the morning peak, you get a little bit smooth, and then you accumulate it again in the afternoon. So you have all this kind of trend. So that is a typical model. You can use LSTM to model that, and then to capture the spatial bit. So we use CNN. So in this way, we combine LSTM and the CNN. So then you can have put them together, weighted them together, and then you have a final outcome. So this is the hybrid model. So details you can find in this paper. So that's the one, but this is still grade-based. So how we can move from grade-based to graph-based, okay? So then later on we say, okay, this is not accurate enough. People don't work on grades, they have to work on the networks. So, excuse me. So we say, okay, actually, we could move to networks. So how we represent it? So look at this graph here. We know, as we said, we can define the spatial adjacency. So if conventionally, most neural network, they call this is a full connected network. That means every node is connecting to everything. However, we think, say, actually, the node 10 is only associated with these few nodes. So this is the first order adjacency. So we can say we want to make the spatial relationship kind of captured into the neural network in this way. So what do we do? Of fitting a model, we say, okay, this is locally connected. We only say hidden layers. We only connecting those nodes all spatially adjacent. So that's how we define the hidden layers. So in this way, the spatial orders somehow be kind of putting into those hidden layers. So this also will speed up slightly the computation. And more importantly, this can make the network convergent much faster. So this is spatial. Again, we put so that's how we did it. So we have, again, we still divided the patterns, the temporal patterns into recent, daily, and weekly. And then this bit is the spatial bit. So this is a graph neural network, and then we sum them up. So this is, again, this is in this paper. So this is great, okay? So as I said, this is really purely focused on the spatial bit. So we think, okay, actually we can make the temporal bit stronger. So that's another one. Actually, we did is we see why not we capture the temporal patterns in our LSTM pattern, and also we use residue LSTM. Basically, if you're doing any neural network analysis, the residue make the convergence faster again. And then we develop, we define the graphic convolution operators, which have some special arrangement to make the weight sharing much faster. So we put them together, and this is an integrated space-time network-based modeling. So again, you can read the paper again. So in this way, we moved from the grid to graph, from graph to space and time graph, okay? And so let's have a look over this case. So we tested this algorithm because for transport, there's normally speed prediction or flow prediction. So we use two examples. One is the data in Shanghai, one is the data in America, because we want to use the open data. So let's just look at the result. So although it's a little bit small, but just look at this. I think this one showing, as I said, the top one shows you the speed prediction. The bottom two talk about the flow prediction. So the very first actually show you about the prediction result. Okay, this is the speed. So let's look at the major this one. Okay, this one really show you the arrow. Okay, so our own result is the red one. Okay, so the red line is our arrow, and the rest are the other models. As you can see, the arrow of our model is very close to 0. Okay, and also importantly, that this one is the kind of about the speed. Okay, you can see the highest or lowest. So that means this model can also capture the peak. As I told you, the challenge is how you predict those peaks without very far away from the baseline. So we capture that. Okay, so for the flow is very similar. Again, you can read the paper yourself for further details. So that's transport. Again, for if anyone is ready to graph neural network learning, they know the graph can be made not only in spatial domain, can also in spectral domain. So that's another model we developed. So again, it's used graph, deep learning, and also we use spectral, and also we fit in the direction of the flow into the model as well. And more than that, we use what we call the inception mechanism to make the weight training much faster. So this is the work we're very proud of. I think this is the top downloaded paper of that journal last year. So if you're interested, please go to check the details there. So this is the moving from statistical approach to deep learning of the network-based forecasting. So for transport, I want to give you another few examples. So of course, I want to talk about our work, one of the work. We have done many others, but this is one. We want to say, okay, we have done so many models. Can we predict the spread of the COVID-19 virus? So Mohammed is the leading author. He's a PhD student with me and James. So what do we do? Okay, please remember this is a very early work when there's not much data available. So we only have a number of the cases. Okay, so we make some assumptions. We think, say, the virus is spread based on historical value, and common to its labeling countries, and the spatial relationship between different countries is dynamic. Okay, remember we said that the relationship should be dynamic. And also, of course, it could be based on the geographical location at adjacency, of course, also transport accessibility, and also government policy. Okay, so we think there's strong correlation between the demographics and the spread of the virus. So what we use, as I said, at that time is very limited data available. So we use the data from the Johns Hopkins University. Thanks to them, I mean, we are all using their data. So we try to model 282 countries. And we use the data set, majorly population, and then, of course, the population density and the urban population, and also use the fertility rate representing young population. Because from our finding with other work, I think the commuters actually is a major factor in terms of mobility, spread the virus, and the young people keep a key role in that. And the third, government controlling strategy is very important, and Oxford has done fantastic work, and they define 30 indicators to representing government's response. Okay. However, third, we really don't have the data on national or international traveling flows. Okay. So that means no mobility data is really able to be combined. So how we do it? So again, we make a graph. Neural network is 282 countries. We define them, and we, of course, it's a fully connected network, but we define adjacency metrics based on the global distance. And we use non-short-term memory, this LSTM model, to capture this long-short trend. And more importantly, as we said, this spatial dependency structure is dynamic. So we use what we call the variational autoencoder to learn this, okay? And this model can output the prediction from first to 1 day to 10 days ahead. That's the structure of it. And again, the paper is online, so if you're interested in it. So look at the result. I think it's promising. So we started off 25th of January, which I think is 2 days after lockdown of Wuhan. And then at that time, there's not many cases, as you can see. And after 40 days, it's kind of started, but actually really after 60 days, it's actually UK is locked down on the 23rd, exactly 2 months after Wuhan lockdown. So the model start fitting the curve. So the red line is the real data, the blue line is our prediction. So from this graph, I will say it's fitting the curve very nicely. However, when there's low data, so this is difficult. So that means when the not possible if the curve tailed down, getting calm. If the second wave come, can we pick it or not? I think probably quite a challenge, because if there's no data, you cannot know the trend. So that's one example. Another example I want to say is talk about the networks for everything. So what about other cases, not only transport? So graph, I hope you show you as a polygon become point. This one is our very latest work. We want the modeling environment data. So we want to focus in rainfall of Lake Basin. This is Lake Poyang Lake. Poyang Lake is in Jiangxi province. It's one of the largest freshwater lake. It's showing here. Okay, so this lake have several rivers around it. The branches, 5 rivers actually. Yangtze River is the larger one, but we separate it. So how we do that? So we divide it. We model the graph of individual lake. So that's how they be represented based on the direction of the flow. We put them as a directed graph. And then we also want to make a graph for the whole lake area. So these are all the rainfall observation stations. Okay, those. And then we will link those lakes with those rivers as well. Okay, so basically we use our simulation to really understand the direction of the flow. Then we model them. Okay, as you can see, for example, at this branch, actually the water comes from here, this very small point, go to this point here, and then they actually have when the level of the lake is low, so the water go to the lake, and when the water of the lake is high, actually the water can come back to the sub branch. So that's why we have a directed graph. So again, how to model it? So we use the graph to representing the the adjacency, and then we use seasonal patterns, daily patterns to use the LSTM to model them. So that means it's a hybrid model. So this is the spatial bit, this is the temporal bit. Okay, so I'm not showing the result because it's progressive. Okay, so that's all those cases. So what about some sparse process like a crime? So there are a lot happening everywhere. So that's actually most of the challenge in terms of deep learning. We have many models like self-exciting point process. We have the STSS. We have lateral KDE. Okay, so all of them has been trying to solve this problem. Conventionally, I think most of you guys say this bit, or some people say this. Okay. So actually, we want to move to Network. We have done that. Actually, we've done that one, make Network based, which thanks to ours, Toby and Gabriel. Also, we have solved this Network based kind of density. So even so we still think that's quite hard to infer the parameters and the time consuming to train. So now we want to develop a deep learning for sparse process. So what's the challenge for that? They're not only sparse in time, they're also sparse in space, right? There are a lot happening everywhere. And also how we can take the network topology, okay? And also in terms of forecasting, we call it imbalanced regression. So how we do that? Again, you can have network, nothing new. This is road network. It's the same as we did before, but we want to put, because of the crime happening around the network, those green dots, we want to put them into the network. So we slap them into the network and then use the middle point as the load of the graph, okay? So then all the things that happen around this segment then become the singular on this graph. So that's how it's being represented. Again, how we define the weight matrix. Then you have so many ways. This is one way we do. Actually, this weight definition has been used hugely on a Keynote-based analysis, and also actually I think has been used in GWR in all these different kinds of forms as well. And it's one of the typical way how we define for the distance. Okay, so that's how we define the networks and the weight matrix, and then it's a long process. I'm not going to talk all about it, but that's how the final be sorted. So what has been doing? So basically, again, we have previous input. So basically, that's what's the say different times that it's the daily one. So it's day one, day two to day whatever. So normally we need about 6 months of data as input, okay, as a minimum. And then we use what they call gated network. This is to capture the temporal patterns. So why it called a gated network? Because they use this gate strategy to emphasize those patterns which have the crime happened. Because the sparsity, it means lot of zero observations. So we use this one to get a temporal pattern. And then for spatial, as I said, spatial is also very sparse. We call the localized diffusion network. This needs to be like we emphasize the first order, second order, or further the spatial adjacency. So to make a full use of the spatial adjacency to capture the spatial patterns. Okay, and then we put them together, and then we do the learning. For the learning itself, we call the imbalanced learning. What does it mean? It means to say for those places or those time who has the crime, we give them a higher weight. That means imbalance. Okay. So in this way, we put them together, we can make the prediction. This is a hotspot, so say higher possibility have the crime. So this way, it's kind of a hybrid model as shown here. We have spatial, have temporal. So in this way, we solve this problem. So this is a very challenging problem, but yeah. So there's lots of other strengths of these models. They can work on very large network and it's very fast. So let's have a look. So this being an example we use for crime, but actually the method can be used for almost all kinds of sparse event, traffic incident, fire incident, or even epidemics. So this, again, we use open data. This is in Chicago, South Chicago. So this is about almost 2 years of data that is showing very, very dense on this small graph. But this is 2 years of data, okay? This big graph show 1 day data of different types. There are 3 types here. So to say the accuracy, we compare with our latest ourselves, actually is network-based KDE, okay? So that's the highest accuracy. So how to compare it? So just let's have a look. We're showing what is happening during that day. So for example, in Birkbeck, so that day we have 1, 2, 3, 4, 5, 6. Okay, 6 of them in total. So the blue line is the one. So basically, how we show them? So this red line, the little red line, shows the hotspot. This the top 10 segments or rows have the highest chance that a crime might happen. So that means that if the crime does happen on those lines, that means we catch it. So that means they're hated. Okay. So if you look at this, 5 out of 6 we capture them on this hotspot, but 1 of them are missing. So we call our hit rate is 5 out of 6. So that's our approach. Then when we look at this network-based KDE, so again we look at them. Actually, half of them out of 6 are missing, and half of them. So this hit rate is 50. So 50 is a very good outcome, but 5 out of 6 is even better, isn't it? So in this way, we think the network-based, graph-based, or called gated local diffusion network based model, but do even better than network-based KDE. So again, this paper has just published. You can read it further if you are interested. So I think that ends my examples of network-based prediction from transport to current virus and to river rainfall prediction, and then to sparse to crime. So now I want to give a few minutes about other work that have been done with networks. I think one of them is to do network-based clustering. So clustering has tremendous usefulness for many things. So again, for network-based clustering, so again, we can use crime as any hotspot prediction. So everyone knows this. Hotspot mostly use the cannon density. They put them into grade to say which bit have highest chance. So or have a high aggregated cases. So they are the hotspots. Again, we can put them into networks. So those red lines are the hotspots on networks. So this is 2-dimensional. But if we talk about space and time, so we will know this one. Space-time statistic has been used widely to do to capture the clusters in space and time. So what it does is just use a cylinder scanning from smaller size to big size, and then equally do from small size in time, and then make it larger in time too. Okay, so that's expanded from space and also to time. It's used a cylinder. Strictly speaking, it's not a cylinder. Actually, it's a cylinder made with the cube as a space-time cube is basically used based on the grades. So again, we can move them to network. So that's what we have done with what we call network-based prospective STSS. So we move them to network so that all the scanning is based on networks. So in this way, we can really capture the hotspot on networks. Okay, this is based on the clustering. This is slightly different from what we did before. It's based on prediction. So conventionally, this is done with the cylinder, and then you have is those grades. It's the grades. Excuse me. So that's one. We use space-time scan statistics Another example, very popular in 3D clouds, is user density-based clustering. Again, two-dimensional. You have original points. You can put them into clusters. Okay. So you all know that. So again, we move to space and time, and then we have space-time DB scan. So basically, what they do is they scan them in space. So what I'm showing here is the GPS data of 300 policemen in Camden. So we put them into as a 3D points. So we do space-time DB scan. And then we can find out what we call the spatial-temporal region of interest. So when they project it to the space, you can say they have concentrated not only in space, but also in time. So this is you can have a small space projected to, and then you have a timeline. That means you are highly concentrated region of interest for those policemen. Again, we move to network. So we can do network-based DB scan. So we can really find out there are activities around the networks, this slide, and then we put them into visualization. Of course, I think Yusuke is the expert in these 3D world maps, and so this is the 3D world maps. Okay, and again, if we projected them to spatial, they actually focused on the networks. So in this way, you can really say, oh yeah, where you go, which street the most focused on or patrolling. So this is the clustering. And then again, for optimization, I think or a simulation, I think we have done lots of work on that. Early work is Ed Manning has done agent-based simulation around the networks for London-wise travel behavior. So this is work by Fanfa. He has done PhD on the optimization of patrolling. So the first problem will be how we balance the patrolling district. Okay, so conventionally, again, grade-based or regional-based, area-based, and again we move to network-based. So in this way, you can say the networks are divided in several different colors, means the kind of patrol areas. So again, this papers there. He also, so in this way, he used what called the Bayesian and based patrol strategy. It's a multiple optimization. We want the patrolling is efficient and flexible, means to say you can have more staff or less staff, and it's scalable. And also when the incident happens, so the police force can easily move to deal with those emergencies, and the rest of the work can be covered by the rest of the team. So there's lots of criteria to balance this whole patrolling routine. So he generate or patrolling and have a system. So basically, we want to have a balanced how to get rid of yeah. Let me see if I can get this run. Okay. So basically, he developed a patrolling strategy. So basically, policemen come off the station and they do the according to the hotspot, which is showing on the right, the hotspot display on the right top. So this is the red line means the hotspot, the police patrolling according to those hotspot, and then cover. So most of the time should spend on this hotspot and they deal with the emergency. So yeah, they also talk about different strategy of patrolling, and yeah, you can on different routines. So this is hotspot. So how can you have a balanced patrol routine? So he can have a different strategy. You can say different color representing different team. So they have more or less the same walking distance, and also they have, as I said, they have other characteristics as I just described. So again, this is all published. If you're interested, you can read it. Sorry. So I think I want to give you a final one. So because those of things maybe all of you guys do, I think probably this one, lots of people do, because that's relevant mobility. This one is another one about the traits. Okay. So lots of work has been done to using traits to analyzing people and the place. So this is the work by Jun Tao. He's done work PhD on social traits with places. So he proposed to use a location-based approach or a lane-based approach. For lane-based approach, you can see this paper at the bottom. It's there. So here we collected the data of the whole London. We just used the case, show you the bit of the Camden. That's where UCL is. UCL somewhere. Sorry, I got my cursor out again. UCL is somewhere here. Okay, you see this blonde here. So okay, so this is of course is a bit old now because now we all the whole trace called the geo-target trace is getting more difficult. So of course, I think you guys are very familiar with we can associate trace with the census units. So these are census tracts. So we can see which area is most artistic area. So it's around here. Okay, it's very close to UCL actually, and then we can also associate it. So basically it's British Museum, okay, because it's in between here. So then we can also use the grade base as most people do. So this is as I said, the modifiable area unit problem. The grade size can change. You can have different grades, so the result may change. But equally, we can associate them with the networks again. So most artistic area again, and also use trace. Okay, this is a Soho. So this is British Museum. And of course, this is our transport hub, King's Cross and Euston. So in this we can say, but really, if you want to go to pub, you can know where you go and food, which street you should go, not just the area. So another one was a lot of works. Okay, you can see we can use this lane, link them up, use Latworks. So this is really shows about, say, like the King's Cross has been mentioned in different places. Okay, which place mentioned not the lane. So that's what it shows. Of course, I haven't got time to mention about other works. I think another visiting student is Dr. Trudy. He has also use graphs. We're trying to do some interpolation, use graph deep learning as well. So as you can see, the application of Latworks could be really broad. To summarize it, I hope, say, in the era of Internet of Things, Latwork-based analytics is needed, especially for urban studies. I already show you how we can use deep learning for space-time prediction, and also Latwork-based approach can be used for clustering, optimization, and analysis. Of course, more real-world application can be applied. I also showed you the case in transport, in crime, in epidemiology, and in rainfall studies. And of course, this also covers about the mobility-related work, routing problems, and the trait analysis. So, of course, there's more can be done. So, in terms of future, of course, so I think in GIS, in terms of GIS domain and education, I think we should teach more about the networks, about the graphs, there's graph theories, tools we can use. And below GIS focused on spatial. Spatial is spatial, but actually temporal is also very important. We should have more training in temporal related analysis. So that's why I say SpaceTimeAI should be more than GI-AI. I know you will laugh at me about this, but that's what I really want to say. Yeah, so we pay attention to integrate the space and time, not only geo. Because this is, when we have, with geo, you may say it's very kind of status. I want to use space-time to emphasize the dynamic bit of the geo phenomena or geo process. So for SpaceTimeAI, of course, most of the model, as I say, is hybrid model, although we showed you some of integrated model. Terms of that, I think still the structure is quite complicated. Can we have a simplified model? And also new tools should be further explored. Deep learning, we're just in the early stage. Graph learning is also early stage. And more importantly, reinforcement learning should be really be used for optimization. I know Professor Adamani now is in it. They have done some about using reinforcement learning about the space syntax or spatial navigation and many other options. There's a group in computer science UCL. They use reinforced learning to optimizing the taxi allocation, or how we can use it for traffic light control. It's really, really exciting topics. We could look at it as well. So of course, there are many more we can do. I think without further ado, I want to thank my team here. I only show a few of them. This is all my very recent PhD students. When they have doctorate, means they just graduate. More new ones here. And special thanks to this for visiting exchange PhD or researchers. They're working with us here. And yeah, so thanks for all the fundings. Of course, I haven't mentioned about other co-Is working with me, courses, and the second supervisors with them. So this all should be thanked. So I think I will end up here. Thanks again for you guys to join me this morning, and thanks to James and Andrew for organizing this wonderful online conference. And thanks for their tremendous efforts. And I hope you will enjoy this. And I look forward to your talk, and I look forward to the other keynotes. So the program sounds very exciting. So thanks again. Thank you. I end up here.
Great. Thanks, Tao, for a wonderful keynote. A virtual applause for you. And now we can open the floor to the two questions. So if you have a question, please type it into the chat. Try to make it as clear as possible. Yeah, I can see that the applause is happening quietly.
So let me see if I can go back to your guys' board. Okay, can see the chat.
Yeah, I'm monitoring the chat in case questions are posted. Still applauses, very long virtual applause. So as we wait for questions, I had one about the policing work and predictive policing. And I remember that a classic problem in that field is that if you have effective policing, you're effectively displacing crime or reducing crime in some ways. And the assessment is quite difficult, because if you change your policing strategy, how do you make sure that your new policing strategy is actually working, depending on how you measure success?
And thanks, Andrew, for your question. I think this is a question I think many people might have as well, so it's a very good question. So in terms of the displacement of crime, I think it's a kind of question I think policing will ask a lot. So in terms of the algorithm, what we did is to say we try to predict where the crime might happen. So if the police take our advice, so they will focus on those areas to patrol. Okay, so yes, you may say those criminals may notice that they may shift to other place, but once they shifted, the data will be reflected. So our tool will also predict what's going to happen next. So in this way, so that means police will always appearing in the places where the crime might happen. Okay, so in this way, they should reduce the crime in the area. So now come to your point. Your question is to say, if police focus on this area, they use my tool, and then the crime may be committed in other place, which might be true. But if the other place also use the same tool, that means they are also able to tackle it in the same way. So I personally think that displacement in this way is not because of the tool. So strictly speaking, display of the crime will happen no matter what tool you use. But if say we have more intelligent tools, actually can make the police response to this displacement much faster. So because any movement, any change of the crime patterns be reflected in your algorithm, because your algorithm pay more attention to the latest trend. So in this way, it does improve the efficiency of policing, minimize the impact of displacement. Yeah.
Yeah, interesting. I think you showed in the talk really well how deep learning and the recent machine learning advances are reshaping these fields. We have a question from Nick Behrman saying, you mentioned we don't have MAUP as an issue. Are there any other issues we should be aware of instead?
Sorry,
so for example,
what the issue he mentioned? Sorry, I didn't.
So he said, you mentioned we don't have modifiable area unit problem.
Yeah. Okay. Yes. So thanks for the question. I mean, for networks, I think the MAUP problem is really minimized. I mean, networks, strictly speaking, I mean, depending on the scale of network, you can always say, okay, but in this way, I think they are minimized in this way. So what's the problem with the networks? I personally say the two are kind of quite limited because conventional GIS started from point line polygons, even 9 we say with network, but the two about networks is still quite limited. And in terms of computational power of network, we haven't been really fully developed in this deep domain. So what is the challenge? As I said, majorly is the topology. Strictly speaking, topology seems quite simple, isn't it? It just you put them in the weight matrix. But how to work on this weight matrix? Actually, there's so many tools. So as I said, they can do spatial one, you can do spectral one. So then for the graph itself, there's so many properties we haven't able to be fully explored. So the challenge is to say, how you represent them as representing them as network is not a problem. But then you define your weight matrix about how to make use of this weight matrix. That's one thing. And more importantly, how you capture the temporal correlation, the spatial correlation on the network. That's what we use weight matrix. But how you really accommodating dynamics is the problem. And the further one, the network itself, the structure might change. Okay, think about telecom network. They can become dynamic network. Dynamic means that the structure might change. As I said, the dynamic spatial weight matrix, the structure might change, the adjacency might change, and also the weight might change. So that's kind of the challenge, I think. But if we can have two can really capture them well, that means we solve the problem.
Yeah, thanks for that. We have more questions flowing in. I'm aware of time, so we'll just take a couple of extra questions. So one question is, would another issue be edge-centric networks?
If I understood the question, you mean to say we use the edge to represent the problem? So in our case right now, we think for the any phenomenon, the process is majorly happening on the edge. I think we use the edge representing the vertex on the network-based analysis, because we have to emphasize the load is something have the signal to do that. So telecom, definitely you can use that, and of course lots of recent smart meters or all those things. I mean, with the autonomous vehicles, they have used those kind of communications. I think they're all tons more applications you can think of it. Transport, telecom, and I think on top of telecom. You can develop many more networks, I think.
So we have another one final question about sparsity. So how does sparsity affect network-based prediction?
So the fundamental of the two model deep learning, okay, if you guys are really on the area, no matter is CNN or LSTM, they are all called continuous learning. So what that means continuous, I don't have time to talk about today. So it means to say we talk about the transport, we talk about the flow, or even about the cases of the virus. That means there's a continuous observation on those points or segments. So even say traffic, sometimes you may say have low flow on it, but we still think to say, yeah, the more or less most of the time you have observation. Okay, so sparse really means those random, we could say random events, although they have spatial temporal pattern like a crime, like a traffic incident, like a fire incident. As I said, IB swarm of those small events. So the challenge for that, when you do the learning, you have to convert those sparse into continuous learning. So that's what we call use the gate strategy. We use local diffusion networks to try to turn those very discrete or sparse data into a kind of a continuous function so that you can learn of it. I think this has been described in our paper. Of course, I think Yang is also here in the audience. So if they need a further discussion on that, we're more than happy to do it.